Let's take a look at a few more example problems involving the intersection of lines in R3 or 3D space. The first question we're going to look at here asks us to find the intersection of the following pair of lines. We have R1 with 1, -2, 4, plus T, 5, -1, 3, and our R2, our position 3, 6, 7, plus T times our direction vector of 3, -2, -4. And just to avoid confusion, I'm going to label the parameter separately in the second line. So instead of T, we're going to have S. And just as a friendly reminder, this isn't labeled on here for some reason, but S and T are elements of the real. And the first thing I'm going to check here right away is that the direction vectors are not parallel. So step one, we're going to consider direction vectors. Direction vectors. We want to check, is M1 a scalar multiple of M2? So let's do that right away. I'm going to have my M1. So the direction vector from line 1, 5, -1, -3. And I'm going to have my M2. Direction vector from my second line, 3, -2, -4. Let's check if they are scalar multiples of each other. So 3 over 5 equals -2 over -1 equals -4 over -3. Those don't look equal to me, so M1 is not a scalar multiple of M2. So these lines are not parallel. And so what are our other options? So not parallel, so either they are skew, so they do not intersect anywhere, but they are not parallel. We could put they're in 3D space, so that's fine. Or there is one solution and they will intersect somewhere. Next up, we're going to put our lines in parametric form. Let's make that a little more clear. So we're going to go from our vector to our parametric equations. So let's write out each line in parametric. So we're going to have x equals 1 plus 5t, y equals -2 minus t, z equals 4 minus 3t. That's our first line. R1 and R2. We're going to have x equals 3 plus 3s, y equals 6 minus 2s, z equals 7 minus 4s. And don't forget to define our parameters. T is an element of the real. S is an element of the real. Okay, cool. Now what? Well, we know that if these lines intersect, there's going to be some point that lies on each line. So the same point lies on each line, and that same point will satisfy the equation of line 1 and satisfy the equation of line 2. So a point on both lines must satisfy the parametric equation of both lines. So if the lines intersect, we should be able to find values of s and t that satisfy the following linear system. So we're going to set the coordinates, or the x, y, and z components of each line together and solve for s and t and see what we get. So let's define that in our steps on the side here. 3, we are going to equate our coordinates. So that's our x, y, z. And we're going to solve for parameters. So s and t. All right, so I'm trying to see if, I'm assuming the x's are equal if they exist at the same point. So we're going to have 1 plus 5t equals 3 plus 3s. The y's should be equal, so -2 minus t equals 6 minus 2s. And the z component, 4 minus 3t equals 7 minus 4s. All right. let's tidy these up. I'm going to collect my like terms and everything. So I'm going to end up with 5t minus 3s equals 2. I am going to have negative t plus 2s equals 8. And I'm going to have negative 3t plus 4s equals 3. So I'm going to have my equations. I'm going to work with equation 1, equation 2, equation 3. And now we need to solve for s and t, and this is where we do our substitution or our elimination. We've had some nice questions before where they get tidied up, like the s or t kind of canceled out or had a 0 coefficient. So I knew right away what s or t was. That is not the case here. So we're going to need to do some substitution or elimination. And this is still part of step 3, so we don't need a separate step. Let's go ahead and work through this. And I think I'm going to work with equation 1 and 2, and I'm going to eliminate t. So I'm going to have equation 1 plus 5 times equation 2. So equation 1 is just going to be the same. It's just chilling there. 5t minus 3s equals 2. And then 5 times equation 2, negative 5t plus 10s equals, that looks a little awkward to read, plus 10s equals 40. And let's add those together. 5 plus negative 5t eliminates the t. Negative 3s plus 10s. Remember this, so I'm like adding this whole thing. Negative 3s plus 10s is 7s. And 2 plus 40 is 42. So if we rearrange and solve, we find that s is equal to 6. I'm going to sub that back into one of my equations. So what I'm going to do is I'm going to take this, sub it into equation 2. So negative t plus 2 times 6 equals 8. Negative t plus 12 equals 8. Negative t equals 8 minus 12, which is negative 4. Or in other words, t equals 4. All right, so I have a value for s, I have a value for t. Now I'm going to plug these back into my parametric equations and see if I get the same point for each side. So step 4, we're going to test our parameters. And what I'm going to do here is I'm going to just test the parameters in my third equation. So equation 3. This is step 4. So let's write our equation. Left side, right side. Right side is equal to 3. Left side is negative 3t plus 4s. Let's plug our values in. Negative 3 times 4 plus 4 times 6. Negative 3 times 4 is negative 12 plus 4 times 6 is 24. And negative 12 plus 24 is 12. Left side does not equal right side. So these values do not satisfy both equations. Therefore, there is no solution. So the lines must be skew. So we know they weren't parallel. We determined that early on. The options are that they were skew, so they're like above each other, they don't intersect, or they intersect at one point. We just did our calculation to find our point of intersection, and there was no value that allowed that to be true. It was impossible or inconsistent. So therefore, there's no solution, and the lines must be skew lines. Next up, we have two equations. We're just going to modify this slightly so that the parameters don't have the same value. And remember, s and t are elements of the real. And let's copy our steps down and kind of follow through basically the same process again. And let's start with step 1 and see if our direction, or see if these lines are parallel by using the direction vectors. So we have our direction vector m1 is equal to 25, 5, negative 10. And our direction vector for line 2 is 5, 1, and negative 2. And you might see a pattern there already. but let's do our calculation. 25 over 5 equals 5 over 1 was negative 2, 10 over negative 2, and those all equal 5. So therefore, we see that m1 is equal to 5 times m2, which means these are parallel. Lines are parallel. And we just need to determine our two possibilities. Are they distinct? Do they lie separately? Or are they coincident? And do they lie on top of one another? And in your note, we can kind of think of it, or we can just have a sketch real quick. Distinct, or remember, coincidence means they're lying in the same location. And in this case, we can do a little bit less work than last time. So we don't need to convert everything like before. I can test a single point that lies on the line. So basically, we're going to check and see if a counterexample is true right away. So it is sufficient to test one point. If the lines have this point in common, we know they have all points in common. Because if they're distinct, there's never going to be any values that are the same. So if I check for my point here, it will not exist here. P1 cannot equal P2. But if they're coincident, P1 is here, and my next line comes through, it will cross that same point. So we're just going to choose a point from one of the lines and test to see if it lies on both lines. So we don't even need to follow all our steps from last time. We'll test a single point. And we can do this because we know that they are parallel, and we just need to discern between being distinct or coincident. So step 2, we're going to test one point, and the point I'm going to use is the position point, or the position vector from the first line. So negative 1, 2, 3, and those are my x, y, z values. So let's put our equation, the second equation of our line into parametric form and test. So we're still doing a little bit of the work from before. All right, so line 3, let's have our parametric, or line 2, let's have our parametric equations. So we're going to have 1 plus 5s, 3 plus s, 5 minus 2s. And let's sub in our values. I guess maybe I was a little hasty canceling out our steps. We're still doing the same, just in a simpler way. So we're still going to equate the coordinates. Solve for s. So we said x is negative 1 equals, oops, and I forgot something on my parametric equation. Let's go back and fix that really quick. All right, I've added my x, y, and z. So let's write our first equation. X is equal to, we're testing if negative 1 exists there. So equals 1 plus 5 times s. Rearrange and solve for s, and we're going to have negative 1 minus negative 2 equals 5s. So s equals negative 2 over 5. And there's different ways we could solve this. We could plug this value into my y and z values and see if they compare. So basically, I could take this value, sub it in here, and sub it in here, and see if we get these x and y values out. I'm going to try this a slightly different way, though, and I'm going to solve for s in each equation and see if we get the same value. So my next one, my y value is 2 equals 3 plus s. S is going to be 2 minus 3, or negative 1. Uh-oh, that doesn't look good. And last one, z has a value of 3 equals 5 minus 2s. 3 minus 5 is negative 2. Negative 2 divided by negative 2 is s, so s is equal to 1. You see, I'm getting a different value for the parameter each time, so these values do not satisfy this equation. So therefore, we'll conclude, therefore, we know that the point negative 1, 2, 3 does not lie on the line R2. And if you check the completed copy of the notes on our Brightspace, you'll notice there's a slightly different method used to answer this question. That's totally fine. I just wanted to mix it up and do it a little differently. Therefore, we know our lines are parallel, which we proved early on. And because the one line does not lie on the other, or the point on one line does not lie on the other, we know that the lines are parallel and distinct. All right, cool. Moving on. On to our third example. Once again, we're asked to check for the intersection of these lines. What do we know about them? And as well, we're going to change our parameter s, and don't forget to define, that these are both element of the real. All right, let's start by considering our direction vectors. So I'll have my M1, 5, 1, 3, and we'll have our M2, -1, 2, -3. We can see right away they aren't scalar multiples, but actually, I won't even bother doing the math. We can tell right away that if I divide these numbers, I'm not going to get the same quotient or k value. So M1 is not a scalar multiple of M2, and so we know these lines are not parallel. So I have two options. Either they're going to intersect, one solution or consistent, or they are going to be skew and inconsistent, and there are zero solutions to the system of equations made by these two lines. Step 2, let's find the parametric form of each of our lines. So my line R1, and I'm going to remember to write my x, y, and z equals this time. Well, let's plug in our values. So the parametric equations for line 1 are going to be 3 plus 5t, 1 plus t, and 0 plus 3t. And for line 2, x, y, z, we're going to have 4 minus s and 10 plus 2s and -9 minus 3s. Now that we know our parametric equations, step 3, we're going to equate them. So I'm going to set my x, y, and z components equal to each other and rearrange them a little bit. So we're going to have 3 plus 5t equals 4 minus s, which is going to give us 5t plus s equals 1. And we're going to have 1 plus t equals 10 plus 2s, which if we rearrange is going to give us t minus 2s equals 9, and 3t equals -9 minus 3s. Rearranging gives us 3t plus 3s. I don't like that. Let's tidy that up a little bit more. 3t plus, 3s equals -9. And we'll label these equations 1 and 2 and 3. And now we need to solve for s and t, and we're going to do that using substitution or elimination. None of these tidied up too nicely, so I'm going to go ahead and use elimination. So I'm going to have equation 1. I'm going to do -5 times equation 2. And then I'm going to add those together. So I'm going to have 5t plus s equals 1, and -5t plus 10s equals -45. And I'm adding these together. Or I could have multiplied by 5 and subtracted. But like I said, depending on who your previous teachers have been, they might have told you that we always need to add. So multiply by a value that makes it negative, so they cancel out. Whatever way is comfortable to you is fine. We're going to eliminate the t's here. So I'm going to have 1s plus 10s is 11s. And I'm going to have 1 plus -45, so -44. So my s value is going to be -4. We're going to sub this into, we'll sub this into equation 2. It doesn't really, I'll sub it into equation 1 and solve for t. So, not 4t, 5t plus s, which we just said was -4, equals 1. 5t equals 1 plus 4 is 5. So t equals 1. So I have defined or solved for each of my parameters. Now we're going to test these values in with my z component and see what we get. So this was step 1, 2, 3. Step 4 is testing. So let's label this step 4. I'm going to have left side, right side, and I'm using my z equation right here. So let's plug those values in. Right side is equal to -9. Left side is equal to 3t plus 3s. Let's sub in our values. 3 times t is 1, plus 3 times s is -4. Gives us 3 minus 12, gives us -9, and left side equals right side. That means that our values satisfy these equations. That means that this point lies on each of these lines. So, therefore, we have a unique solution when s equals -4 and t equals 1. So we've proven that there is a solution. We just need to actually find it. So in order to find the value, we're going to take one of our sets of parametric equations. It doesn't matter which one. So I can either take these equations or these equations, sub in my values for t or my values for s, depending which one I decided to use, and let's find that single point. And I only need to do this for one of these sets of equations because we're finding the same point. We're finding where they intersect. It doesn't matter which one I use. I'm going to get the same values. I'm running out of room here. Let's see if I can find a little more space for us to finish this up. All right, we're just going to have to write carefully as we finish this up. So step 5, we are going to find the solution using R1. So let's plug in our values. X is equal to 3 plus 5t, and we said that t is equal to 1. So that's going to equal 8. Y is equal to 1 plus t, which we said is equal to 1. So it's going to be 2. And z is equal to 3 times t. So 3 times 1 is 3. So therefore, our point of intersection is 8, 2, 3. And we could also, if we wanted to, could also test our R2 line with our s value, just to confirm we get the same point each time, but it's not strictly necessary, just an extra test. So what I'm going to go back here and just add to our steps. So test the parameters, and then finally find POI by subbing our values. By subbing our parameter into our parametric equations. Really running out of room here, sorry about that. I'll just zoom in a moment so we can see our steps. So we considered our direction vectors, determined if they were parallel, went from vector to parametric, equated the coordinates to solve for our parameters, tested our parameters in the third equation. We had a consistent result, so we knew that these lines intersected, and then we found the point of intersection by subbing that parameter back into one of the sets of parametric equations. And if we wanted, we could have also done it for the second set as well, but it wasn't strictly necessary, so we didn't. So I'm going to zoom out so you can see the whole thing all at once. If you want to pause and work through this again, great idea. Otherwise, we're ready to move on. That is going to be all for this video in terms of calculation. If you are following through in the notes, you'll see our next section is talking about GeoGebra, which is an online 3D graphing calculator tool we can use for visualizing and calculating, kind of just like using Desmos, but I will make a separate video on how to use that and how to access that.